All right, thanks a lot, Amir. So first, let me thank the organizers. Yesterday, with too much vodka, I couldn't do a proper toast, but it's been such a pleasure to be here. The conference is beautifully organized. The city is wonderful. Of course, I guess you didn't contribute to that, but the talks have been wonderful. So thanks very much for allowing me to be a part of this. So that said, let me jump to the talk. What's the agenda today? This is based on a bunch of joint works. Hopefully I'll say the names again, but if not, the slides are online and you won't remember it anyway. The agenda is to give you a technique for, in which, so it's a technique which can be applied to a certain class of combinatorial looking questions, but the technique goes via algebra, and in some cases the algebra is sort of surprising how it's coming up. And the technique, I'll call it the polynomial or the interpolation method, and later we'll refine it further to call it the multiplicity method, and that's where the title comes from. The agenda is the technique. It's not these problems, but these are the problems to which we will apply them. I will describe this list decoding problem very briefly, very quickly. That will be the motivating example. And then most of the talk will be talking about these things called Kakeya sets and getting bounds on them. This is a sort of an interesting combinatorial geometric kind of a question, but the real interest for computer scientists came from certain construction of extractors, which was in fact, I think, proposed by Amir in joint work with Zeev Dvir. And this will be the thing that we really wanted to get to, but we'll keep trying to talk about the problem in this context of the Kakeya sets to say, well, we want to develop the technique further, so let's explain it in this context. One other area where this multiplicity method has found applications is locally decodable codes. I wasn't planning to cover it here, but very fortunately Sergey covered it for you yesterday anyway. So you saw something about the word multiplicities there. It's the same multiplicities, it's the same idea, and the applications that we will talk about will be complementary. All right, so what's the list decoding problem for Reed-Solomon codes? Let's start with what are Reed-Solomon codes. These are very commonly used codes. I mean, in fact, probably the most dominant codes in practice are these ones. Why? Because they appear on every storage device that you have, digital storage device that you have. And the way they work is you have some message that C0, C1, C2, and so on up to C sub D are some bytes that you want to code or something. You think of these as elements of some finite field F. And the encoding of this message is you sort of think of conceptually of the polynomial represented with these as the coefficients. So m of x is this algebraic object, and the representation that you choose for this algebraic object is by its values. So you just evaluate it at all the points in the field, let's say, and write them down. Okay, and why is that nice? We know that polynomials disagree very often if they are different. So a low degree polynomial cannot be 0 too often. Two low degree polynomials cannot agree too often, and that turns out to be a very useful element in the performance of these codes as well as in their sort of algorithmic abilities. The decoding problem, so this is what would be the problem that arises naturally when you think about using these codes and then some of these bits get corrupted, or some of these bytes or these field elements that you write down get corrupted. So you wrote down m of alpha for every alpha in the field. What you see is m of alpha for most alpha and some arbitrary values for other alpha primes. And the way I'll express that problem is really, the x1, x2, and so on are the various elements of the field. You know which ones these are. I also knew which ones these are. I wrote, let's say, the polynomial values at all these m of x1, m of x2, and so on the disk. And you read them, but then there are errors when you read them. So you read y1, y2, and so on to y sub n. Now you'd like to know what is the polynomial m. And this turns out to be a very simple geometric question. You have these pairs of points, x1, y1, x2, y2, and so on to xn, yn. You know the degree bound d. And what you would like is the polynomial which passes through as many of these points as possible. Okay, so in other words, you want the m such that m of xi equals yi for at least t of these points out of n. Okay, this is the decoding problem. Now, the list decoding, what does this phrase refer to? It says that if the number of errors, meaning the number of points where m of xi does not equal yi, is very large. So think of it as 1% of the data is correct and 99% is wrong. Okay, so that's kind of a setting. Then many polynomials may actually fit with 1% of the data. Okay, there could be up to 100 easily by just taking them to be disjoint sets. There may be more. And the list decoding problem says report all such polynomials. Okay, we'd like to do this in polynomial time. Let's say polynomial in n amount of time. Well, you can't do this in polynomial amount of time if the number of polynomials which agree with 1% of the data is exponential in n. You can't report all of them, period, right? This number is just too large. So the related combinatorial question is, can there be many polynomials? You just, this is not an algorithmic question at this stage. Merely, if I tell you that these are the parameters, n is such and such, k is such and such, d is such and such, and t is such and such, how many polynomials? Okay, and we would like to come up with some conditions on these numbers which says that the list size L is bounded. So this is the question we have. Suppose for contradiction or whatever you assume that there are polynomials p capital 1, p2, p3 and so on to p sub L, L polynomials, and each polynomial has an associated set S sub I. P sub I has a set S sub I where it agrees with the thing. So S sub I is a subset of these x1 to xn's. And the combinatorial question is the following. Can we manage to make each one of these sets large? Each one of these should have at least t elements while keeping the union of these sets small. The union of these sets is at most n, right? Can L be very large, SIs be very large, while n is relatively small? Okay, so can this really happen together? So this is the question. So again, you're given L polynomials. These are the sets. Each one of these sets is of size exactly t. Let's say it's a subset of these given points in the space. How small can this number n be? And this is there's an algebraic analysis that we gave in these two works, which forms the basis of the decoding algorithm also. You can analyze these questions purely combinatorially, and there are simple combinatorial proofs of the statements that I will prove. But the algebraic analysis, which is the one that I will give, is much more useful in designing decoding algorithms. So let's go ahead and look at these proofs. And the proof idea turns out to be extremely simple to describe. Okay, so we have these n points in the space. And what we will do is find one polynomial q in two variables, x and y, which is not identically 0. Okay, keep this in mind as we go along, whose degree is not too large, at most L in y and at most n over L in x. Okay, so this is some parameters such that q of xi yi equals 0 for every I that's given to us. Okay, so every point that's given to us in these things, q of xy is 0. Okay, why these parameters? Well, these parameters allow us to prove that such a polynomial q exists. Why? You look at the number of coefficients that you're seeking. How many coefficients have I got to find out? The number of those coefficients is L plus 1 times n over L plus 1, okay, which is a number greater than n. So that's the number of degrees of freedom that you have. The number of constraints that you have is n, each one of which is saying q of xi yi equals 0. Okay, there are n constraints, n plus 1 variables, and each one of these constraints is a linear constraint on the coefficients that you're seeking. Okay, the coefficients that you're seeking, on them, these constraints are just linear constraints. So you have more variables than constraints, so there is a solution. There is a non-zero solution. Okay, these are even homogeneous equations, so obviously there is a solution which is everybody is equal to 0, but we don't want that, but there's also other solutions. Okay, once you have these other solutions, you can even find them algorithmically, but we don't care about it right now. And immediately it implies that okay, so if the number of points that we are seeking, and this is an algebraic condition one can prove, I won't prove it today, but it's something that can be proved easily, that if the number of agreements that you have where yi, yj equals p sub I of xj, if this quantity that you get is very large, larger than the sum of these two degrees, sorry, n over l plus d times l, okay, where d was the degree of the polynomial that you're seeking, then you can prove that y minus pi of x, this algebraic function divides that algebraic function, q of xy. Okay. Why is this useful? Well, you know that a polynomial of degree L cannot have more than L different factors. Okay. Unique factorization is applying. And so you immediately get a bound saying, well, the number of different PIs that satisfy this condition is at most L. Okay. So you can conclude immediately that, well, you know, if this condition held, you would have too many factors. L, you know, you have L different polynomials, P1, P2, and so on to P sub L. This polynomial has degree strictly less than L, but you will end up having needing L factors. So this condition in turn cannot be true, and once you have that, you sort of invert it around, etc. You get n is at least that quantity. Okay, and so in particular, this tells you that if the list size that you're looking for is very large, greater than t over 2d, then n would need to be very large, and the contrapositive gives you the bound on the size of the list that you're looking for. Okay. So the focus of this talk is to look at the underlying method that we saw here, and I'll try to describe it without the numbers over here. So if you want to understand some algebraically nice set capital S, in this example that we just saw, the set happened to be the set of points in the plane through which you were trying to pass too many polynomials. If you want to understand this set, then what you first do always in this method is you find some polynomial that vanishes on this set. This polynomial should have low degree. How low should the degree be? What exactly are the definitions? Well, it depends on the context, but you would always want to keep this as low as possible. Okay? And almost always the statement first says, well, you can prove the existence of this polynomial just by counting. Why? Because the thing that you're looking for are the coefficients of this polynomial, and the constraints are linear equations, homogeneous linear equations on this thing. Okay? So this part of the technique is fixed. It's always the same. And the next thing that we do is we use the algebraic niceness of this set. So in our case, the set happened to be the union of many polynomials. Okay? That's algebraically nice. Use this algebraic niceness somehow to prove that this polynomial q actually happens to vanish in other places as well. So in our case, we claim this saying whenever y happens to equal pi of x, including the points in S, but also points outside of S where this which satisfy this condition will be zeros of this polynomial capital Q. Okay? So Q was designed to be a low degree polynomial. It was supposed to vanish on some given set of points that were given to you, but because the set was nice, Q is 0 on many other places as well. And once you have that condition, well, you know, this is a low degree polynomial and it's having too many zeros. The zeros that were given to you, I mean, obviously would not have contradicted anything, but the extra zeros that you were able to prove contradict something. So, and that immediately says that, look, the set S could not have been too small. Okay, so something like that. So in this previous example, it was saying, let's look at the union of all of these d polynomials. How large was the set? It's very large. Okay, it's larger than the number n that was promised. So this is what we will call the polynomial method, and this, by the way, I should say that this sort of this is an abstraction that sort of is retrofitted to based on Dweer's work, which was a brilliant piece of work, which we'll talk about in a few minutes, and so on. But so it's not as if this is how the picture looked from the beginning, but this is how it looks now. So let me now try to introduce the concept of multiplicities. So what I talked about right now, this is what we call the polynomial method. Okay, so we'll now try to develop it further and make it a little bit more sort of stronger. In this example that we will describe, it will be very mildly stronger, but it will start becoming very useful in the later applications. Okay. All right. So one sort of underlying theme at the time of this work was that, look, what the union bound, the bound that we prove that the size, if you take all of these sets and take their union, they should be large, was something that we could have proved easily by an inclusion-exclusion argument. Each one of these sets has size t. Any pair intersect very rarely because these are both points where a degree d polynomial passes through them, so the intersection size is at most d. And you immediately you can apply the inclusion-exclusion argument to say, well, the union must be very large because the sets are large and the intersections are small. But what we had was an algebraic argument proving exactly the same thing, but it was algorithmically useful. So we wanted to say, well, can we do something better? Are there better combinatorial bounds, and can we match them? And it turned out that there is a better combinatorial argument which says that the sizes of these sets should be large, which works even when the inclusion-exclusion argument fails, but we could not match that algebraically. And that led us towards this thing. I'll try to emphasize the numbers less and just the principles, and just trust me that the numbers work out better. And the idea that over here was, well, okay, so far we tried everything we could and it didn't work, so let's try the following thing, which is completely unmotivated. Instead of finding this polynomial q which passes through every point, we'll try to find this polynomial which passes through every point twice. Okay, so why? There was no intuition for this, merely that it's an interesting exercise. So you ask this question, so what does this mean to pass through a point twice? And from Sergei's talk, you all know that you should have the polynomial should vanish at the point, and its partial derivative with respect to x should vanish, and the partial derivative with respect to y should vanish. Each one of these is a linear constraint. So you have 3 linear constraints, and that 3 leads to this quantity 3. It says that, well, if you do the same counting and ask how large should the degree of this polynomial be, well, in y we want the degree to be less than L because that's the contradiction we are seeking. And so the x degree we will need to allow up to 3n over L. Okay, and now you have enough coefficients to handle 3n constraints, which is what you have. And then you have sort of some counting argument which says that, look, because every time you have this y equal p sub I, yj equal p sub I of xj, you actually found 2 zeros, 2 points where this curve meets this curve. Okay, why 2? Because the multiplicities that we chose were 2. And that says, well, as long as twice t is greater than this parameter over here, then you get some contradiction. And so you sort of go around, etc., do the calculations. Eventually you find out that you can get a bound on n, on the list size, even when n was somewhat smaller. Over here you needed, n was somewhat larger. Over here you could not get a bound when n was greater than t squared over 4d, but now you can go up to t squared over 3d. A little bit better. And you sort of work harder and harder with increasing the number of multiplicities. It goes all the way to n squared over 2d, and or actually even sort of you fuddle with the parameters a bit more and look at the polynomials of slightly different structure. You go down all the way to n squared over d, which was somehow a holy grail at the time. It led to fairly interesting results. Let me tell you very briefly about it. The results, so overall, all we managed was getting something like go from t squared over 4d to t squared over d. Was this really important? Turned out it was actually very important. At the time, this was the first time that we could get an interesting improvement to decoding of Reed-Solomon codes for codes of rate greater than 50%. Rate of the code is, say, is the sort of the degree of the polynomial to n. And why is this interesting? Because most of the codes used in practice have rate around 90%, and all the previous algorithms were working at rate much less. This thing turned out to be even more interesting in more recent results of Guruswamy and Rudra, but I won't talk about it, and I want to jump ahead. I want to tell you about, so what is the method of multiplicities? So the method of multiplicities is an abstraction of the example that we just played with. It says to analyze the size of an algebraically nice set. So again, same, what is the algebraic niceness of the set? In this example, it was a set which is the union of L evaluations of L polynomials. Okay, so that makes it algebraically nice. We find a polynomial which is 0 in the set, but now with high multiplicity. That's the only difference. And you prove the existence by the same counting arguments, and now you use the algebraic niceness to prove that S vanishes at other places as well. Okay, and once you've proved that it vanishes at other places, you find out that you have a low degree polynomial which is 0 too often, and you're done. Okay, this is the method of multiplicities. So the only change compared to the polynomial method is now we're just saying, well, when you find the polynomial, it should be 0 with high multiplicity on this set. Okay, and for some impenetrable arguments, this has very often been a better, gives you improvements on the thing without the multiplicities. And this remains a mystery to me today, and just works, so we're happy with it. So now maybe I should say a little bit more precisely what a multiplicity is. I don't think I will really get very precise till the very end, but I'll sort of try to tell you a little bit more at each stage. Over the reals, like we said, it's just the partial derivatives should vanish. And in particular, if I say, it's a multiplicity, q of xy has a root of multiplicity m plus 1 at some point, if every partial derivative of order up to m vanishes. So you take a derivative with respect to x, with respect to y, etc., etc. And we will do derivatives with respect to other number of variables as well. Over finite fields, the thing that changes is the definition of a partial derivative. It is no longer the standard derivative, but something called a Hasse derivative. And the reason this comes up is if you're working over a field of characteristic 2, for example, take the second derivative, in the standard sense, it's always 0. Of any function, you take the second derivative, it will be 0. Hasse derivatives sort of prevent this from happening. So, these are somewhat nicer. And what these are, I'll come to later, but, for now, all we'll use is for a while is the following fact, which is that there are, if you ask the question, so if I have an n variate polynomial, how many partial derivatives do I have to consider to get a root of multiplicity m plus 1? Well, there will be m plus n, choose n such derivatives. Okay, so this is just, you take all these derivatives in different ways, and it's the number that pops up. And each one of these derivatives is a linear function of the coefficients of the polynomial that you're looking at. Okay, so linear function, of q, whatever. Okay. Yes?
Just to make sure, you want the root to vanish at point AB, right?
Right, sorry, vanishes not at 0. Wait, sorry. So when it should vanish at AB, correct, sorry. So I've given this talk about 3 or 4 times, the first time somebody's pointed an error. All right, so that's what multiplicities are, and now what we will do is apply them to this concept called Kakeya sets, and let me describe what these are. Let me give you the definition first and then briefly tell you what it's interesting for. So a set, so these are subsets of n-dimensional vector spaces. You can define them over any field, but here I'm going to define them only over finite fields. So this F is a finite field. If I don't mention it explicitly, little q will stand for the size of this field, capital F, okay? So I have a subset of this field, and we call it a Kakeya set if it contains a line in every direction, okay? So a line, formally would be defined as the set of points of the form x plus t times y, where t ranges over the field. X and y are vectors, t is a scalar. And what do we mean a line in every direction? When you specify a direction called y, you should be able to find a starting point or a offset x such that all the points of the form x plus x, x plus y, x plus 2y, etc., are all contained in the set that you're thinking of, okay, that you have. So it's an interesting question. So it's sort of geometrically, if you think about it and over the reals and so on, it's an intriguing concept, you would say. Shouldn't it need to be pretty much the whole space in a sense? And surprisingly, no, that you don't have to have everything, but the question of how large should these be turned out to be a very interesting question. So our interest, as I said, is finite fields, and in particular we are interested only in lower bounds. And a very obvious and simple counting tells you these two things. Well, this is, I don't know how simple, whether I can even call it counting. So obviously, if you take all the points in the space, then you have a Kakeya set, and that gives you an upper bound of q to the n. Just by using the fact that given a set of size capital K, you have at most capital K square different lines, that tells you that, look, this set better be of size roughly q to the n over 2 at least. Okay, maybe I'm missing some constants, but roughly that. So the question is, can we do better than this? This is the exponents are off by a factor of 2. Can you do better than this? And it turned out that this question was actually wide open for a long time. By the way, the question is an interesting, aesthetically very pleasing question. Versions of this question over the reals were over the rationals maybe, or the reals, I don't remember. Reals were of great interest in additive combinatorics, and people had related these questions to other questions that they had been studying. Over the finite fields, I think it was an interesting exercise for them, saying, look, do we have techniques to understand this? Let's try to create the finite field version of the question, not necessarily hoping for expecting progress. And the best that the bounds went were from, instead of n over 2, the bound went up to something like 0.51 n or something like that. Okay, so something very tiny. And this remained the case, and with fairly heavy duty techniques. And then in 2008, Zeev Dwyer came up with this beautiful argument, which you will see gave you just the perfect answer. Okay, so what was Dwyer's analysis? Let me just go through this thing, and then it's the polynomial method. And by the way, the reason this looks very similar to the method as I described earlier is because the earlier description was based on this slide. Okay, so don't get fooled by the thing. This was, the problem was open for a long time, and suddenly when you see such a simple analysis, you have to realize, it didn't come out of nowhere. So what was his idea? So the polynomial method, right? So what does it say? You have an algebraically nice set. What is the set? Well, it's a set of points in this finite, in this vector space, which contain a line in every direction. That a line in every direction is some algebraically nice property. Let's see if we can apply the polynomial method here, and obviously the answer is yes. So we'll find a polynomial capital Q which is not 0. As the formula says, which happens to be 0 on the Kakeya set, okay, on every point in the Kakeya set. And we will insist that its total degree be at most the size of the field. Sorry, so Q less than Q is a sort of terrible notation, but this is the way things work out. And let's say its degree happens to be D. So we'll use little d to denote its degree, just in case you were very lucky. Typically, you expect it to be of size q minus 1, because you insisted it should be of degree less than q, it will be q minus 1, but maybe it's less. And the counting says that, look, if the set, the Kakeya set that you're examining, where you want lower bounds, if this thing turns out to be too small, less than something like q to the n over n factorial, then such a polynomial exists. How do you prove that? You count the number of coefficients. I've specified the degree of the polynomial. Now you can, some simple combinatorics tells you how many coefficients are there that you're trying to find. If the number of such coefficients is more than the number of constraints, then you have a solution. And how many constraints do you have? As many as the size of the set. So if the set is of small size, then a low degree solution exists. Okay? And turns out that, with some amount of work, one can show that if the degree d part of q, the highest degree part of this polynomial q, will vanish at a point y, any point y, which happens to have the feature that if there is a line in direction y that is contained in k. Okay, so just suppress what you know that there is a line in every direction. If there is any one direction y in which you can find a line in direction y that is contained in capital K, then the homogeneous highest degree part of this polynomial will be 0 at y. Okay, it's a slight twist on the polynomial method, but And why is that? Well, you look at this line, you say, well, let's look at this function capital Q restricted to the line. It's a polynomial of degree at most d. Okay, but it's a polynomial in one variable. And this polynomial is identically 0. Why? Because on every point in on this line, this polynomial evaluates to 0. So this polynomial is identically 0, and it turns out that even though this the highest degree coefficient of this polynomial capital Q sub L is the homogeneous part of capital Q evaluated at y. Okay, just write down the formula for it. That's what it turns out to be. So once you have this, well, what do we have? But now we have a line in every direction. E is contained here. So for every point y, the highest degree homogeneous part of this polynomial Q is evaluating to 0. But the highest degree homogeneous part of Q is a non-zero polynomial. Okay, that's all we care about. And it's a non-zero polynomial which is vanishing everywhere in the space on Q to the n points. So immediately you conclude that this polynomial must be identically 0, which is a contradiction to the assumption that you have over here. Okay? So you conclude that this statement, we said, well, let's assume that the set is of small size. This must be false. And so we have a lower bound on the size of any Kakeya set. And look at the exponent, it's n. Okay, so we went from q to the n over 2 roughly to q to the n with a one-page argument. So this is a beautiful, brilliant result. So what else remains to be done over here? Why the method of multiplicities? Well, it was mainly to say, well, can we do anything better? In particular, well, here is this n factorial. Can you do something about this n factorial? And can we see what else how else we could improve it? Okay. So this is something that we played with in a paper with Shubhangi Saraf, who was a graduate student at MIT and now at IIS. And we said, well, maybe we should try to find the same formula, find a polynomial that vanishes often. And this was a non-trivial guess to make, but it worked out perfectly with this guess. We said, well, for some reason, the multiplicities that we'll use is n, the same as the dimension of the space that we are working with. Okay, so it turned out to be a fairly good choice. And we'll find a polynomial q, which is not identically 0, whose individual degree in each variable is less than q. Okay, so this is a little bit more space. Previously, in De Veer's argument, the total degree of the polynomial was less than little q. In our case, we will allow high degree terms, but as long as the degree in each variable is not more than q, is not q or more. And well, so how many coefficients do we have now? Well, this is very easy to count. It's just q to the n, right? So the total number of coefficients that we have is q to the n. And we will want to make sure that at each one of these points in the Kakeya set, this polynomial vanishes with multiplicity n. okay, with high multiplicity, multiplicity n. So if you recall, we said there are m plus n, choose n partial derivatives to worry about. What does that number look like in this case? Well, it's 4 to the n. Okay, so 4 to the n times the size of the Kakeya set. If it's less than q to the n, then we have more coefficients than the number of constraints, and so you can find such a polynomial. So now that you've found this polynomial, what can we do? When we look at this polynomial and restrict it to a line, you get a pretty high degree polynomial. In each variable the degree is n, is q. There are n variables, so that all you can say on an arbitrary line is that your degree is like q times n, strictly less than q times n. Okay? But that's okay, because at each one of these points you have a 0 of multiplicity n. And there are q such points. So one concludes that whenever you look at this polynomial and restrict it to this any line, a line that's contained in the Kakeya set, it's identically 0. Now you can just plug back to Zev's analysis and conclude that the highest degree homogeneous part of q is 0 at the direction specified by the line, and so you have q to the n zeros of a polynomial which should not be 0 on the entire cube. Okay, so we have the contradiction, and one concludes again that this assumption could not have been true. So the size of the Kakeya set should be at least q over 4 to the n. Okay, so we gained a little bit here. So let me just sort of contrast the numbers. So the very simple analysis says it's at least q to the n over 2. Dweer's analysis says it's at least q to the n over n factorial. Now, the real interest in this question was really q tending to infinity and n some constant. So this is an improvement, but not always. So there are choices of q and n where this is not an improvement, but now what we have seems to be an improvement pretty much almost always, right? So it improves simple even when q is a large constant and n is going to infinity. So you get something interesting even here. And after we looked at this, we sort of started comparing with known upper bounds of this thing. How large can these Kakeya sets be? And turns out you can get some upper bound better than q to the n. You can actually get something like q to the n divided by 2 to the n minus 1 or something. So some exponential loss was necessary. Some exponential loss is all that's going to happen. Okay, so this thing has to be of the form q to the n divided by some constant to the n, and that constant is somewhere between 4 and 2. Okay, so this is roughly where we left this question, and then Dweer came to us and said, well, can we do even better? And the reason turned out to be that it was very interesting and related to these extractor questions. So let me see how the thing, so I will now take a bit of a digression, introduce the problem which motivated the final question over here, but then answer only the final question. I will not tell you how the solution translates to this other thing. The reason I want to talk about this problem over here and in general is because it's a beautiful area of work. It's been going on in our field for many years. And the kinds of ingredients that both go into it and come out of it have been very pretty. So let me at least give you a few lines of my perspective on it. So I will not, so there are some concepts called extractors and mergers, and the bottom line was we wanted to see, can we improve them? And let me tell you what these objects are, or even sort of give you a general sense of where these objects come from. So the general theme in computing is always, we want to understand or design algorithms which sort of start with some x and produces output f of x. And in randomized algorithms, we say, well, take a large random string and also send that to the algorithm and see how can you design these algorithms that work this way. Now, when we say algorithm, so the perspective I want you to think about is not that you're feeding a random string, but really that you're feeding a distribution to this algorithm. It's not, the algorithm only gets to see one random variable from this distribution, sample from this distribution, but really its analysis is measured as a function of this distribution. And now the question is, where are you going to get these random variables, uniformly distributed random variables from? And there is a randomness production industry that's going on in the field of theoretical computer science. And what this industry does is produce various forms of randomness processes. Their input is some distribution A, their output is some other distribution B. And their performance is measured not by looking at the string here and saying, what string did I get here? But rather by saying, if I gave you a random variable from this distribution, what would it come out looking like? What would the randomness look like? If this was a collection of very, very, very correlated random variables, can I make this look like uniform? But in general, all kinds of variations of the questions are being asked and analyzed, and it's a beautiful thing. I mean, really, these algorithms never see the distribution, they never produce a distribution, but their analysis always asks the question, what is this distribution, what is that distribution? Okay? And everything that you sort of study in the field of pseudo-randomness, pseudo-random generators, extractors, limited independence generators, epsilon bias generators, condensers, mergers, and others are all objects of this nature. Okay, and this is a beautiful thing, and one of the eventual goal is to say, look, let's start with some readily available randomness, either because it's got very, very little real true randomness, or because it's sort of physically easy to generate, and make sure that the eventual output is uniform. Why? Because then you can sort of ship it off to the industry which designs randomized algorithms and let them use it. Okay? So there's a huge collection of beautiful results here, and one of the questions that we were interested in was the design of extractors. And let me tell you what extractors are. Extractors are algorithms that convert dirty randomness to pure randomness. Okay? So what is dirty? It's the bits that you get are biased, they are correlated, they have various forms of thing. The formal definition usually talks about having sufficient amount of entropy, minimum entropy, the min entropy, but these things are not, by no means are the input bits uniform and independent. The goal is to produce pure randomness, which means every bit should be independent of the other bits and they should all be uniform. We can't do this deterministically, so we'll allow a small amount of seeding. You can get a little bit of randomness if you want, but not much. If you want to produce n bits of randomness over here, you can take log n over here. Okay? That's roughly the game. A different object which was used in a particular construction of extractors was this thing called mergers. It's also in this industry of randomness processors. It's one of these objects, ingredients. What it does is it takes k random variables, and produces one. And what we are told about these k random variables is that one of them is actually uniformly distributed, nice, just the way you want the output to look. But we don't know which one. And furthermore, the other k minus 1 may be heavily correlated with this one. They may be identical, they may all satisfy some summation condition, etc., etc. No guarantees on the others. And we would like to produce from this either a uniformly distributed random variable or something with high entropy. Okay? So, and again, we will allow ourselves a little bit of seed. And the question that Zev was interested in was to try and design, and this came from work, I think, with Amir, with you, right? Yeah. So they had a specific construction of mergers which they wanted to understand, and to understand that you really needed a better understanding of the Kakeya sets, or techniques which could do better with the Kakeya sets, even better than q over n divided by 4 to the n. Okay? So that was the question. So we wanted to do better. So roughly, what was the state of the art prior to our work? You could do this merging. It would take you roughly log of n random bits to do the merging, where n was the length of each one of these random variables. Each one of them is uniform on n-bit strings. What we were able to get after our analysis was log of k. Okay? You have one of these guys is uniformly random. So if you could pick one of these guys that takes sort of at random, that takes log k random bits, and roughly that suffices. Okay? So that's the theorem. But so there was a merger analysis, etc. I won't get into it. And the concerns for merger analysis basically said that, look, so far we have techniques that work as long as the field size is greater than n, but we really wanted to consider situations where the field size was really, really small and n was going to infinity. So, and the same kind of questions can be asked in the KKA sets, and so we wanted to understand why were we stuck at q over n to divide by 4 to the n. Can we do even better? So what was the obstacle to this multiplicity method? So let's see, why can you not, why did we stop at multiplicity n when we were looking at these KKA sets? Okay, I have this points in space, and why did I stop at multiplicity n? Suppose I gave you that at every one of these points you have a polynomial of multiplicity 10 times n. Could you have done anything better? Well, I claim it's useless to know more. Why? Because so far the only feature that we've been using is that this polynomial will eventually vanish at many, many places. How many places can I make it vanish? Well, maybe entire space, q to the n different places, everywhere it vanishes. If it vanishes everywhere, well, the only condition that I can, it's vanishing at q to the n places, but the most I can extract from that is that if this polynomial happened to have degree less than q in each variable, then I can say something. If it's allowed to have degree more than q in some variable, and I know it's vanishing everywhere, well, it doesn't mean anything to me. It doesn't help me. These things do exist. There are polynomials of degree q, x1 to the q minus x1, which vanishes everywhere in the space. So if you tell me that it vanishes everywhere in the space, that doesn't give me much if this polynomial is allowed to have degree more than q in any one variable. But if it has degree at most q in every variable, then that's a polynomial of total degree n times q. And so getting n on each point on the line, if I get a root of multiplicity n, that's as strong a result as I ever need to use. So if I want to go beyond this point, I really need to overcome this bottleneck, which says that, look, I want conditions under which polynomials have degree greater than q, but I want to conclude that they are 0. So multivariate polynomials which have degree more than q in each variable, and still I want to conclude that it's identically 0 only by knowing something about what this polynomial is doing in the space. Okay, and this sort of, for a while we were just stuck, because it looked kind of hard to say what else can you say? Polynomial has degree more than q. Well, what should we really say? And turned out that the right thing to have asked was, well, suppose we will try to prove not just that the polynomial vanishes at every point in the space, but at every point in the space it vanishes with multiplicity 2. A multivariate polynomial is vanishing at every point in the space with multiplicity, say 2 or 3 or 4, etc. If you can utilize this fact to somehow conclude that this polynomial should be identically 0, that would be useful. So in order to go there, we need something like a Schwartz-Zippel lemma, but extended to allow for multiplicities. And that turned out to be the key quest. So maybe we can hopefully somehow show that the polynomial q vanishes with high multiplicity at each point, and maybe we can also use this. So both of these were maybes, and then in the work with Dwyer, Koparty, Saraf, we actually were able to implement this plan. So let me tell you a little bit about how that goes. So a little bit more about the multiplicities. So the multiplicity of a polynomial q at some point is, this is just notation for saying how often does it vanish at the point a. So a is a vector, n-dimensional vector. Q vanishes at this vector a with multiplicity m if all the partial derivatives of order m minus 1 are 0. And let's just use this sort of this indicator variable which says that is this polynomial 0 at a or not. Okay, so notice that this indicator variable can be expressed as the minimum of 1 and the multiplicity of the polynomial, right? So if the multiplicity is 0, that means the polynomial does not vanish at a, and so this quantity should be 0. On the other hand, if the multiplicity is anything greater than 0, then in particular q of a is 0, and so this indicator value satisfies this algebraic expression. Now the standard de Mello-Lipton Schwartz-Zippel lemma that Amir talked about and we use all the time, says the following: if you take any subset of the field and look at how often, so when I sum up over all A in S to the n, ask how often is a polynomial 0, and that I'm expressing by this complicated expression I of QA, then this quantity is upper bounded by D times S to the n minus 1. Okay, this is the standard thing. How often can a multivariate polynomial be 0? Well, the fraction is D over S. Now what we were able to do, there is a sort of, there's a simple proof, but I can't remember it, which says that, well, instead of this I of QA, which is the minimum of two quantities, I can just replace it by the second quantity and the identity still holds. Okay, so is there a question here? Oh, sorry. So instead of I of QA, I can just say multiplicities of QA. If I just sum that up over all this, over this box, it will be at most that quantity. Okay, so it's a strictly stronger dominating result. So given that this identity has found so many uses, well, we hope that this other identity, which is not much more complicated to prove and was probably, of course, known many times in the right literatures, now you can use it. This is something that's available to us, and maybe we can find other uses for it. In the case of Kakeya sets and mergers and extractors, it was turning out to be useful. So a little bit more about the multiplicities. So what are these Hasse derivatives? You can sort of formally define it in terms of the coefficients of Q, but the important thing to remember is that it's just some linear form in the coefficients of Q. And the real, there's a sort of a nice clean definition, but I probably won't mention it now because it's a little late in the day. And the important thing that you want to use about it is the fact that the derivatives are linear functions, and this is something that we already used in the Reed-Solomon list decoding. If you have a 0 of multiplicity m at some point and you restrict it, this polynomial q, to a line, then you still have a 0 of multiplicity m at that point. This is something again that was used already in the previous work. Now we might use it for other settings also. Here is something that was never used in previous works but turned out to be useful in the paper with Zev and others, which is that if we take the ith derivative of a polynomial, so where I itself is a vector, so I1th derivative in the first direction, I2th derivative in the second direction, etc., then it's also a polynomial whose degree is at most degree of q. You can get some lesser terms, but its degree is at most the original degree. So derivatives of polynomials are themselves polynomials. Well, we knew this, but we never used this in the past. Now it turned out to be quite useful. And here is where I should this is one of these cases where we said, obviously what we are doing is all right, and then realized that we had forgotten one step in the proof, and that was this one. And this is something that's very interesting to notice. Okay, so usually derivatives satisfy the property. How do you compute the second derivative of a function? You take the first derivative and then compute its first derivative again. That's normal derivatives. Hasse derivatives are not like that. Okay, so this is the one key difference between Hasse derivatives and standard derivatives. If you take the Hasse derivative, well, in the direction I plus jth derivative will not be the jth derivative of the ith derivative. Okay, but it still happens to have one direction of the implication which is useful, which is good enough for us, which was the crucial direction for us. If the I plus jth derivative vanishes somewhere, then it implies that the jth derivative of the ith derivative will also vanish there. The converse is not true. And that's the reason, the second derivative, the first derivative of the first derivative would vanish everywhere if you were working on a field of characteristic 2. But the second derivative need not vanish. The Hasse derivative, the second Hasse derivative need not vanish. Okay? So the converse is not true, but in this direction it's true and it's useful for us. And all of these facts, once you know this, turned out to be very useful for us. In particular, it allows us to conclude the following. If you tell me that the polynomial q vanishes with high multiplicity at some point, and I look at its ith derivative, which is itself a polynomial, it's vanishing with high multiplicity at the same point. Okay? How do you prove that? You just apply this lemma and then you look at the definitions and whatever. Okay, so it's very simple, but it tells you that if I found a polynomial which vanishes with high multiplicities at some point, and I look at its 15th derivative, it's still vanishing with multiplicity m minus 15 at that point. So that's useful. How do we use it? So what we decided to do was to say, look, let's find a polynomial q which has very high multiplicity on this point. So this multiplicity will be going to infinity if you fix everything else that was given to you, q, n, etc., etc., etc. It will still be going to infinity. And once you have this, what happens is we know that for every derivative of order up to m over 2, this polynomial q, the ith derivative, vanishes with multiplicity at least m over 2. Okay? So this is based on the previous slide. Everywhere, if your function is vanishing, then its derivatives are vanishing. In fact, all the derivatives up to the m over 2th derivative are vanishing. Well, based on the previous analysis, we could conclude that q evaluated at some point was 0. At some arbitrary point in the space was 0, not just on the Kakeya set. Now we can use this and apply that same statement syntactically to the first derivative of q, to the second derivative of q, the m over 2th derivative of q, any derivative of order m over 2 of q, you can apply this and conclude they are all vanishing at this point. So we conclude based on that q has a root of multiplicity m over 2 at every point in the space. Okay, so now we are not only concluding, starting with the fact that q had multiplicities of order m at Kakeya set points, everywhere in the space it's turning out that it has zeros, it's vanishing with multiplicity m over 2. So notice m over 2, there's a ratio of 2. That's what turned out to be the key question. So once we had this, we sort of started playing around with the numbers, which I won't do over here, but it's not a thing. You start saying, okay, you find a polynomial which is 0 on the Kakeya set with very high multiplicity, conclude it's 0 on the entire space with very high multiplicity, and then apply this sort of strengthening of the Schwartz-Zippel that we had earlier, and you conclude that this polynomial is having too many zeros of too high multiplicity on the space, and that's a contradiction. What do you conclude based on this? The size of the Kakeya set is q over 2 to the n. Okay, so recall, we know that there are upper bounds which say that this can be as high as q over n divided by 2 to the n minus 1. So we are off by a factor of exactly 2, not some exponent in n, not off by the multiple of n, so not even in the in the constants. Okay. All right, so this is tied to within 2 to the little of 1 factor. This allowed us to get a very strong result for mergers and so on, but I won't talk about it now. It's kind of and I should mention that there are some sort of beautiful results that are not covered over here. In particular, Sergey, along with David Woodruff, had a beautiful construction of locally decodable codes which are different from either of the codes that he described to you yesterday, and they were sort of vastly improved later on, but had a very pretty use of this idea of using partial derivatives even very early on, and multiplicities very early on. We've seen many other applications of multiplicities, in particular this very beautiful result of Koparty, Saraf, and Sergey that Sergey talked about yesterday. And so the conclusions are, it's sort of a powerful technique. It's very simple. It's really, if you didn't understand it, it's my mistake today, but or your mistake by feeding me so much vodka yesterday. But really, these are very, very basic kinds of manipulations of objects, and uses very, very little, but it's proving things which are remarkably powerful. And so the question is really, are there more applications that we can find? Okay, so thanks. I'll stop here.